Hi, everybody. Welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book. And today I'm going to go over a recent daily math problem, which is really the same kind of problem I posted a couple months ago. I don't know if you guys remember, but I posted a video solution on two infinite sums. They were very similar to these. The only difference was instead of 12n, I used 10n. And so for the first time, I had 12n plus 1, 10n plus 1, and 10n plus 9. This time I have 12n plus 1 and 12n plus 11. And then for the second sum, I had 10n plus 3 and 10n plus 7. Now I have 12n plus 5 and 12n plus 7. Anyway, in case you haven't seen that video, don't worry about it. Here's the problem. I mean, let me just skip to the problem. So here's the problem. We want to find closed form radical expressions for each of these following infinite sums. Of S1 is a sum n going from 0 to infinity of 1 over 12n plus 1 minus 1 over 12n plus 11. And then S2 is a similar sum, is the sum of n going from 0 to infinity of 1 over 12n plus 5 minus 1 over 12n plus 7. And if you wrote out the terms explicitly, maybe it'd be a little bit more obvious what we're summing. First one would be 1 minus 1/11th plus 1/13th minus 1 over 23 plus 1 over 25 minus 1 over 35 and so on. And then the S2 would be 1/5 minus 1/7 plus 1/17 minus 1/19 plus 1 over 29 minus 1 over 31 and so on. Turns out both of these sums converge, but you need the negative parts, otherwise they wouldn't converge. But anyway, we want to evaluate these sums. So how do we do that? Well, like I said, I posted a very similar problem a couple months ago. Same method. We can use the same method we used for that problem. We start with this nice identity involving the cotangent. Turns out that the cotangent of z, where you're supposed to now think of z as a complex variable because it doesn't have to be real. I mean, it works if it's real too, but there's this nice identity. This is what's known as the partial fraction representation of the cotangent. You can write cotangent z as an infinite sum. Now n is an arbitrary integer. It could be negative as well as positive. So we're summing over all the integers of 1 over z minus pi n. And you might wonder where this formula comes from. This formula comes from complex analysis. It's pretty beautiful. I've seen a proof of this. And usually the way you do this is you start with a similar expansion. Instead of cotangent z, you start with pi times the cotangent of pi z. And it turns out that this function, this is what's known as an analytic function, or meromorphic anyway. It's analytic except for poles. It turns out that this function has a simple pole with a residue of 1. If you don't know what that means, don't worry about it. It has a pole, which means it's like a place where the function blows up. And every integer has a pole. So we, for that, and then it's well behaved everywhere else. And it turns out that we can just write it as this infinite sum of 1 over z minus n, and once again ranging over all the integers. Pretty beautiful formula, I think. Anyway, so we can use this identity, we can use this formula, equation 4, to evaluate the sums we want. And here's how we do. We have to do a little bit of algebraic manipulation. But we basically start with those formulas. So first we just start with expression for S1. We want to get it into the form where we can use the partial fraction representation of the cotangent that I showed you a minute ago. Maybe I'll show it to you again. Let's go back to it. Yeah, so formula 4, we want to get it in the form of formula 4 where we can use this formula. And here's what we do. Like I said, it involves a fair amount of tricky algebraic manipulation. I did the same thing for a couple months ago when I did the previous problem, but let's just go through all the steps here because it's kind of neat, and you might have to do this yourself at some point. So S1, the definition I gave is the sum n going from 0 to infinity of 1 over 12n plus 1 minus 1 over 12n plus 11. First trick here is to factor out 1/12 from this sum. And if we do that, then the thing inside is 1 over n plus 1/12 minus 1 over n plus 11/12. I think you can see this is more closer to the form we want. We want z minus n. So we just have to do a little bit more manipulation. Another trick is on the third line for the second sum, we can replace the index n by n plus 1. I'm still calling it n here, but now n is going from 1 to infinity instead of 0 to infinity. And now we have, instead of 1 over n plus 11/12, we have 1 over n minus 1/12. Because we added 1 to n. I think you can see that n plus 1 minus 1/12 is the same as n plus 11/12. So I've really just changed the index on the second sum. Well, this is nice because now, well, we have two infinite sums still, and I'm gonna rewrite these a little bit. This isn't much of a change going from the third to the fourth line. I kept the first sum the same. I just switched around the orders of the addends in the denominator. So because addition's commutative, n plus 1/12 is the same as 1/12 plus n. But now if we want to do the same thing in the second sum, if you want to replace n minus 1/12 by 1/12 minus n, then you've got to change the sign, which is what I did here, because before we had a minus sign from the second sum, now we have a plus sign. So I think you can see this fourth line follows pretty easily from the third one. And now we really pretty much have it in the form we want. The next thing you should note is that this first sum, we can just change the index from n to minus n. And then we have a sum going from n equals minus infinity to 0 of 1 over 1/12 minus n. And now we can combine that with a second sum, which has the same thing inside, namely 1 over 1/12 minus n, but for the second sum, n is going from 1 to infinity. Well, and the first sum, n is going from minus infinity to 0, and the second is going from n equals 1 infinity. I think you guys can see that covers all the integers from minus infinity to infinity. So finally, we can rewrite this sum as 1/12 times the infinite sum, and going from minus infinity to infinity, of 1 over 1/12 minus n. Well, we finally got it in the form we want. We got it in the form of equation 4. Let me just go back to that one again so you can see it. Yeah, we got it in the form of the equation on the bottom here, where now z is equal to 1/12. So I think you can see that if we plug in 1/12 for z, you're going to get pi times the cotangent of pi over 12. But don't forget we have to divide by 12 because there's a factor of 1/12 in front of this whole sum. So finally, we get S1 equals pi over 12 times the cotangent of pi over 12. Well, that's really nice. That's a nice formula. And that is a closed form expression for S1, our first sum. And I'm not going to go through all the work again, but you can do exactly the same analysis for S2, the second sum. And if you do that, you'll find S2 is equal to pi over 12, same numerical factor in front times the cotangent, this time cotangent of 5 pi over 12. And the reason you get 5 pi over 12 is because 5/12 is going to replace 1/12 in the final infinite sum. So anyway, that's how you do that. But we're not quite done. I mean, we have these formulas involving trig functions, and those are closed form expressions. A lot of people would be satisfied just to stop here. And in all fairness, if you have a scientific calculator, you can calculate these on your calculator because cotangent is on most scientific calculators. Even if it wasn't, you could use cotangent equals cosine over sine. You might have to convert to degrees. Pi over 12 is 15 degrees. But anyway, you can use these. So these are closed form expressions. But the problem was asking for radical expressions. So now we still have to do a little bit more work. We have to find radical expressions for the cotangent of pi over 12 and the cotangent of 5 pi over 12. And the way you can do this, I think the easiest way to derive these formulas is to use what's called the half angle identity. And it turns out that the half angle identity for the cotangent is equation 7. Cotangent of theta over 2 is just the cosecant of theta plus the cotangent of theta. And if we plug in pi over 12, we get the cosecant of pi over 6 plus the cotangent of pi over 6. And these are easy to, cosecant is just one over sine. I think you guys remember from high school when you were learning trigonometry, the sine of pi over 6, which is the same as the sine 30 degrees, is just 1/2. So the cosecant, which is 1 over the sine, is 2. And then for the cotangent, you may remember that the tangent of pi over 6 is 1 over square root of 3. That means the cotangent is the square root of 3. So finally, you get cotangent of pi over 12 equals 2 plus square root of 3. And if you do the same thing for cotangent of 5 pi over 12, I'm not going to go through all the steps again. Use the same identity, that's just the cosecant of 5 pi over 6 plus the cotangent of 5 pi over 6. That turns out to be 2 minus the square root of 3. So now the last step, we have these radical expressions for cotangent of pi over 12 and cotangent of 5 pi over 12. The last thing we have to do is substitute those expressions back into what we had before, namely equations 5 and 6. Maybe I'll go back to those. Yeah, I think I went too far. Did I? No, actually, we go to this equation. Yeah. So we had pi S1 was pi over 12 times the cotangent of pi over 12. And we just said the cotangent of pi over 12 is 2 plus square root of 3. And then we also said the cotangent of 5 pi over 12 was 2 minus the square root of 3. So those are the things we have to plug in. All we have to do is multiply both of those radical expressions by pi over 12. So we get S1 equals pi over 12 times 2 plus the square root of 3. And if you calculate this numerically, you get approximately 0.977049. It's pretty close to 1. And I think you can see it has to be pretty close to 1 because the leading term is 1. You're going to get 1 minus 11 plus 1/13 minus 1/23, so on. The other terms oscillate, but the other terms are pretty small, so they don't contribute all that much. And then for S2, it turns out that numerically you get approximately 0.0701489. This is pretty small, about 0.07. About 1 over 14 roughly. And I think you can see the sum starts 1/5 minus 1/7 plus 1/17 minus 1/19. Starts a lot smaller. You could combine the pluses and minus 1/5 plus 1/7 is 2/35. And that's pretty close to this answer. And then you get other terms that decrease pretty quickly. So anyway, that's the answer. These are the radical expressions for S1 and S2 and the numerical approximations of them. So that's how you do this. Anyway, that completes my video for today on these infinite sums. Thank you for watching. Long live math, and I'll see you guys next time. Bye.